So good morning, everyone. A warm welcome to this new edition of the ACS Photonics Global Webinar. And today is a special webinar in occasion of the celebration of the 2020 ACS Photonics Young Investigator Award Lecture. And as you know, as you may have seen already in the news, so this year's winner is Professor Maiken Mikkelsen. She's an associate professor in the Department of Electrical and Computing Engineering at Duke University. So really congratulations, Maiken, on behalf of the whole ACS Photonics team. So without any further delay, I will give the floor to Chief Editor Harriet Warder, who will ask a few questions to Professor Mikkelsen in order for us to know a bit more about her and her work.
Okay, great. Yeah, good morning, everybody. And I want to say a special welcome. Thank you, Roman, to Maiken Mikkelsen. Many hearty congratulations. So we'll start with just a short discussion here before we get going with the seminar, because I think it's always interesting when somebody gets to a moment like this where an award is given to learn a little bit about your background. And so I think a lot of people in the community would be quite interested to know, for example, who were some of the early influences that that influenced you to become a scientist and eventually go into photonics?
Yeah, that's a good question. I think it started when I was really young, from my mom always encouraging me to, when I found a flower or plant, to look in a book and see, like, realize which one is it, and recognize the small details and differences, looking at rocks, birds, plants. And then as soon as I was starting to take physics and math classes at school, that immediately became my favorite subject. So it was a very obvious path for me. In Denmark, where I grew up, you have to pick your major right out of high school when you start college, and there was never any doubt in my mind. So, but I had wonderful teachers as well as encouraging parents.
Okay, great, yeah. So thinking about the field of photonics, what would you see over the last 5 years? Of course, we're going to hear from you about your work, what are some of the significant advances that you see in photonics in the last 5 years that are really sort of shaking up our field today?
Yeah, that's a really good question. There's so many great advances. It's hard to pick one, but I'm really excited about how we're moving optical metamaterials into the optical field to make metasurfaces, and really can mold and modify optical properties on the deep subwavelength scale, and how we can start to make computations and much more advanced functions that we thought possible in the past. I'm also really excited about atomic scale 2D materials, how we can really start building things up from the ground up. It is really a new way of thinking about materials and photonic structures.
Yeah, I guess maybe for optics people who are usually thinking on the nanoscale, we can think there's still plenty of room at the bottom, all the way down to the atomic scale. So, yeah.
Yes, and I think we're starting to peek into that. So that's very exciting.
Yeah. So just thinking about for the future, over maybe the next 5 to 10 years, what do you see as being directions? I know a lot of young scientists are trying to sort of think about the directions for their careers. And what are the fields that you see emerging in that time frame?
Yeah, that's a good question. I think some of the directions, some of the breakthroughs that we're seeing in these optical metasurface and atomic scale materials, and merging some of that going forward. And I think it's also really exciting. I think some of the fields are maturing a little bit to see that they might be able to make some real life applications, and trying to evaluate how robust are these phenomena, that we're not just cherry picking one nanoscale structure, but trying to see if we can get control over large areas where it could actually start to to make an impact in other devices. So that's something I'm excited about as well.
So big enough to see by naked eye, even though textured at the nanoscale. Yeah. So,
yeah, exactly. So where the properties are emerging from almost atomic scale dimensions, but where the phenomena can be revealed at the microscopic scale.
yeah. Okay, great. And then finally, I'll just ask what your advice to young scientists would be. What would you tell people, say, entering as undergraduates or maybe pondering going to graduate school? What kind of advice, either about scientific field or just sort of general life advice about life as a scientist?
Yeah, follow your dreams. If you really enjoy it, go for it, and keep remembering that excitement and spark and enjoyment of doing the science, and of course work hard as well to reach these big breakthroughs. It's challenging too, but very exciting, and we shouldn't forget that joy and excitement and privilege it is to be able to do this every day.
Yeah, okay. Well, I think those are very wise words and that we can all carry with us, especially in this pandemic time where I know particularly you as a young parent are working very hard and trying to balance everything in life together. And so that's makes it even more satisfying and meaningful. So what I'd like to do now is to transition to the actual conveying of the award. And the award, of course, if we were at a meeting where we were all congregated, we would enjoy a cup of coffee and a cake, and we would all be in person, and we could shake your hand on a stage. But alas, we're not in that world yet. So I wanted to share with people and offer congratulations and mentioned that Maiken is cited for her pioneering contributions to scientific research in the area of nanophotonics, plasmonics, and quantum optics. So I want to stop for a moment and just offer hearty congratulations to Maiken from the entire ACS Photonics community. So well done, and carry on the.
Thank you so much.
Yes,
so, very honored.
Yes, and we'll have to do the embrace and applause at a time, sometime when we can meet again in the future.
Looking forward to that.
Okay, and so then, without ado, I'd like to offer you the floor to give your lecture, which about atomic scale engineering for ultrafast optoelectronics. So Maiken Mikkelsen.
Thank you so much for the kind introduction and for this award. I'm very honored. And you can hear me all right? Yes.
Yep, we hear you.
So I will talk about how we can move towards atomic scale engineering using deep surveillance, nanocavity structures, and evaluate potential applications for ultrafast optoelectronics. So everything at the foundation of what we're doing is really the fact that we can, by controlling local electromagnetic fields, we can create tailored optical properties. So when you think about, for example, an emitter in free space, it will have a specific absorption and emission rate. But if we put this in a cavity or in a modified electromagnetic environment, we can modify a wide range of the optical properties. We can modify properties such as the absorption rate. How efficiently is this emitter absorbing incoming light? We can also modify the spontaneous emission rate. So after we excite an electron hole pair, how fast do they recombine and emit a photon? And when we are modifying those rates, typically we're also modifying what's called the radiative quantum efficiency. So the likelihood of emitting a photon after such an electron hole pair is excited versus any other non-radiative decay channels in the systems. We can modify the radiation pattern of emission. If you're looking beyond just emitters, we can also modify nonlinear generation, such as second and third harmonic generation, modified local heat generation, hot electrons, hot carriers. So we can really modify a wide range of properties. So it comes to mind to try to probe what are the ultimate limits for these tailored properties. So we can see we can modify them, and their modification depends on the local electromagnetic field. So to see how much we can modify them require us to try to make very large local field enhancements. And we also want to be able to control these phenomena, understand them better. So that means we need very precise control of these local fields. And one way of doing that is utilizing plasmonics, which allows us to concentrate the incoming field beyond the diffraction limit. So the way we can think of this is incoming light is exciting. If you have a metal dielectric interface, as shown here, can excite free electrons in that surface. And these free electrons are oscillating at a particular frequency in the wavelengths of these surface plasmons, or in the case of small metal nanoparticles, local surface plasmons, is much smaller than the wavelengths of the incoming light, meaning we can concentrate this incoming light to very small mode volumes, which is enabling local enhanced electromagnetic fields. It turns out that you can get larger field enhancements if you don't just have a surface or single nanoparticles, but that you have two metal nanoparticles or two metal interfaces close together, such that you have a small gap between metals, as shown in this example with a bow tie antenna and a small air gap here. You can see that red here is indicating a hotspot in this area where there's a large field enhancement. So we can see the largest field enhancements are occurring for small gaps between metals. So then the question becomes, how do we actually realize this experimentally? So these are made using electron beam lithography, and making these tiny gaps is very challenging, and you're really reaching the limit of electron beam lithography, and you will not be able to do this with a single nanometer precision, and you will just smear out effects. So what I started thinking about, and others in the field were thinking about as well, was how can we think about making very tiny gaps between metals, in particular sub 10 nanometer gaps, and have a precision, a resolution with a single nanometer scale. Ways to utilize that is often taking advantage of chemical techniques, as well as instead of looking at a lateral geometry, look at a vertical geometry that allows you to leverage layer by layer deposition methods. So ways to achieve such small gaps in a controllable manner include sulfur sample monolayers. You can also take advantage of atomic layer deposition, and then in this case silver nanowires, functionalize gold spheres here with dyes, utilizing host gas chemistry that also allows you to position molecules underneath. So we can see we have some ways of moving to these very small dimensions, but it requires us to think a little bit outside the box and not use our traditional electron beam lithography techniques that a lot of people from the physics community is starting out with. So that gets me to the outlines. I want to talk about how can we use such nanoscale gaps to do a number of things. So I will just try to give an overview of some different research. First, I will talk about ultra-fast emission from single emitters, but also to centimeter scale areas that I alluded to a little bit in the beginning. Then mention some possibilities of observing strong coupling, utilizing higher order modes and do dynamic tuning. And then we'll talk about some recent work that was published in Nature Materials earlier this year on far thermal photodetection that's enabled by such almost atomic scale structures and also color pixels. So the geometry that we're utilizing throughout these experiments are these gap plasmon cavities that has a small mode volume and large field enhancements. So you can see the structure is schematically here, and the field enhancements on the left. So they consist of these colloidally synthesized nanocubes that are between 50 and 100 nanometers. So we can pick the size pretty precisely. They're very monodisperse in size. And then they're placed on top of a metal film, often gold, but can also be silver, other materials. And then we create a small gap here that consists of a dielectric spacer that can be typically between 5 and 10 nanometers. And we can embed emitters directly in this gap. You can see we have the highest field enhancement in the gap region underneath the cube here, and the field enhancements can get up to 100-fold. You can see we have both electric and magnetic field enhancements. And this is SEM, so you can see these are indeed small cubes. These are colloidally synthesized and single crystalline, but you can also fabricate simpler structures by using electron beam lithography on top. So I mentioned electron beam lithography is not always giving us good enough resolution, so it's not giving us good enough resolution for the critical dimensions, which is the gap here, but the dimensions of the nanoparticles on top is less stringent requirements. And this structure has a strong dependence on both the gap size and the cube size, which means that we have two knobs to control the plasmon resonance. They also have a nice directional emission, so if you have emitters coupled underneath, they will emit to the far field. And we're utilizing this vertical gap and bottom-up fabrication technique, so we can control the gap size on a single nanometer scale. And often what we do is using layer by layer deposition of positive and negative polymer that allows us to build this up with this critical, almost atomic scale precision. So the first thing we wanted to explore about how much we can modify the spontaneous emission rate. And any modification in the spontaneous emission rate compared to free space is referred to as the Purcell factor. And the spontaneous emission rate is really not an inherent property of emitter, but really arises from interaction between the emitter and this electromagnetic environment. And this is critical for enhancing single photon sources, could be useful for modulators and communications. And the spontaneous emission rate here depends on the transition dipole moment and this local density of states, which is what we have access to modifying by changing this electromagnetic environment. So it's really an interplay with the environment and the emitter that allows us to make these designer optical properties. And this has been studied for a long time. This was the original paper by Purcell in 1946. And the change in spontaneous emission rate really is proportional to the quality factor of the cavity and inversely proportional to the mode volume. So these are the two knobs that is traditionally used to modify the spontaneous emission rate. And a lot of work has been done in this area, in particular, originally using all dielectric high Q cavities, very beautiful work using micropillar cavities, 2 and 3D photonic crystal structures, and often at cryogenic temperatures. So these are very tricky to fabricate, requires a lot of hard work, and some of the highest Purcell factors were around a factor of 10 in this case. So we're interested to see if we can use Plasmonics to be able to achieve laser enhancement in the spontaneous emission rate. And while there were a lot of reports in literature already, some reporting high enhancements, some quite low enhancement or even crunching, what was really missing, we thought, was a systematic study to try to probe what are the mechanisms behind and how can we achieve large Purcell enhancement in a reproducible manner and very predictable. So what we found was a control on the single nanometer scale really matters of the critical dimensions. So to explore that, what we decided to do was to vary this gap size between 5 and 15 nanometers. And while we are varying the gap size, naturally the plasmon resonance will change as well. But what we did to account for that was modify the size of the cube such that we could constantly keep the plasmon resonance overlap with the emission. So the dark red here is indicating the plasmon resonance, and the pink here is the fluorescence. So we want these two overlaps so that we on resonance with the emission which is what is giving us the largest enhancement in the spontaneous emission rate. And what we are seeing is large modifications in the fluorescence lifetime. So that's what you see here. So these measurements are done by exciting the structure with a pulse laser here. And then we're using a time-correlated single photon counting to time tag the arrival of the photons, which is what you're seeing here. And then fitting this can then give you the lifetime, the excited state fluorescence lifetime. And we see that there's a large difference from going from 15 nanometers and down to a 5 nanometer gap. So that's, I think, was very exciting, because these were dimensions that had not really been carefully explored in the past. And we can see, compared to the intrinsic lifetime of these ruthenium metal complex dyes and glass, that looks almost flat here. This is very large enhancements. But we also found was that understanding this nanoscale environment is key. We don't just need a single nanometer precision, but we also need to carefully understand other things that's going on. So one thing is we had to understand is the variation of the field under a single cube. So in this case, we're looking at an example of molecules. So we are basically averaging all these different positions. And this is COMSOL simulations showing the variation in the spontaneous emission rate. We also had to understand exactly where these dyes located, because the closer to the middle that they are, the non-radiative rates are modified, and the dipole orientation. So when we take all these things into account, it describes the experimentally observed behavior very well. It allows us to extract the quantum yield here as a function of the gap thickness. And we can see as we go to small gap thicknesses, the non-radiative rates are increasing significantly as expected. But if you add a gap thickness around 10 nanometers, you can get quantum yields around 50%, which is pretty decent for a lot of applications and high for plasmonic structures. So knowing that, now we can go back and from fits to the data here. This is a stretched exponential fit. So it means that what we are seeing is really distribution of a lot of different decay channels. And it allows us to then, from this data, extract the most likely emission rate enhancement at the different gap thicknesses here, which is shown in gray, as well as the enhancement in the maximum spontaneous emission rate, and also the enhancement of the radiative rate, which is the enhancement in the spontaneous emission rate times any change in the quantum efficiency, which I think is probably the most important figure of merit and give us enhancement around a factor of 1,000. So I think we have two takeaway messages here. One is that we can indeed get reproducible, very large enhancement in the spontaneous emission rate. But in order to do that, we really need to have control on the single nanometer scale, which was not, I think, fully appreciated in the community beforehand. And we have to then think about alternative fabrication techniques to be able to get this type of control. You may notice that even if I had these large enhancements in the spontaneous emission rate, we're still not really getting to an ultra fast speeds, because this is still tens of nanoseconds, because we started out with such a slow emitter, which we did to be able to map out these large enhancements and not hit the instrument response function time limits. So next we looked at colloidal calcium selenide zinc sulfide quantum dots. These are very standard emitter that has a lifetime about 10 nanoseconds and are commercially available. So when we are enhancing these, then we are getting very fast lifetimes indeed. We are seeing similar enhancement, almost 1,000 times, but now we get into an ultra fast spontaneous emission rate into around just 11 picoseconds. So this is really pointing towards very fast optoelectronics on the 100 gigahertz, potentially into the terahertz regime. And there could be low power, there could be ultra fast modulators, fast LEDs. This could also be very useful in enhancing II emitters that can often typically be very dim. I want to point out that we're not exciting them at this point at that high rates, because we start to have stability issues for the materials that they can photobleach, but we are not limited by the electron hole recombination anymore. That is happening on a very fast rate. Later on, I will show you how fast can we actually modulate the spontaneous emission rate. Another area where single where fast spontaneous emission is very important as ultra-fast single photon sources. If we're not at the single photon level, we have the choice of using lasers in the sense if we want fast modulation. For quantum information science, we have to stick for single photon sources. So the only way we can enhance that speed is through the Purcell effect. And in this case, we're using a similar experimental geometry, sample geometry, but just using a lower density of quantum dots, such that we on average have a single emitter under each of these cubes. We are doing anti-bunching measurements here that is verifying that we're indeed measuring a single emitter. The way that that is done is that you have light hitting a beam splitter here, and then these photons will act particle light to go to one or the other detector here. So if you have a single photon source, it means it can only emit one photon at a time, because you have to wait for electron holes to recombine, get re-excited. So you have a delay, so you never see two photons emitted at the same time, which is why we see this dip at time 0. So this is indicating that we are indeed measuring a single emitter. We are then doing similar lifetime measurements here. The experimental data is shown in blue here. And we see, again, very fast lifetimes. In this case, it was actually a single exponential decay that's just following the bi-exponential shape of the instrument response function with a lifetime of around 11 picoseconds. And this is pointing to what's very fast single photon sources, potentially into the gigahertz regime. But again, you have to work trying to find emitters that are very stable. And these quantum dots are not the most stable things, but I think it's very exciting that you can use these similar ideas in different material systems. So this is work done by Sasha Balsaseva and Vlad Shalev, where they used nanodiamonds with embedded nitrogen vacancy centers. And they could see for single nitrogen vacancy centers, they could see a 70 times decrease in the lifetime and a 90 times increase in the fluorescence. So I think it's very exciting that these nanogap structures can indeed be useful in a number of systems. And there's another example from literature I wanted to share with quantum emitters in monolayer tungsten disilinite. So these are created by the strain of the nanocubes. I think this was a very clever idea. This was by Stefan Strauss group, where they placed EBL fabricated cubes, I believe, and with a stamp onto the monolayer material, and that induced strain. So the red here is indicating the strain. And on average, you can see the four corners of the cube. On average, it's inducing about 4 emitters per site. And in this case, I observed Purcell factors up to 550, but they're not quite at the single emitter level, typically with 4 emitters per site. But I think it's very exciting ways that you can deterministically embed single emitters. So we were very excited about ways of studying single nanoparticles, single cavities, single emitters. And then we got contacted by the connectivity lab at Facebook that thought that was also interesting, but what they were really interested in was the opposite problem, was how big can we go, how efficient can we go, how many emitters can we pack in here, how bright can we make these materials. So I thought, while that was not how we were typically thinking about things, I thought that was really an important question and an important thing to study. So we collaborated on trying to answer those questions. And what we found was, after some optimization of these structures, we could actually get a uniform response over centimeter scale areas. So in this case, this is not quite to scale. We did increase the density of cubes, but not quite this much. And then we packed in multiple layers here of emitters. So in this case, we use Alpha-532. So this is just a common fluorescent dye. And we can see that the dye in the cavity is much brighter than the dye on the glass. And we had enhancements in the fluorescence of almost 1,000 times, an emission rate enhancement of 130, but that's really just limited by the instrument response function. And also another thing that we typically don't like to characterize is the photon conversion efficiency. So photons coming into the structure and out of the structure without making a bunch of normalizations to under the cube, laws here and there. So After optimizations, we could actually get 30% conversion efficiency, which is into the regime where it could be actually commercially useful. The other thing that's very exciting with fast spontaneous emission, as I mentioned, is fast modulation. So even though we showed one fast spontaneous emission rate, we wanted to demonstrate that you can actually modulate this spontaneous emission as signal. So in order to do that, we used femtosecond laser pulses. So we had one pump pulse here that's exciting at time 0, and then we had another pulse that we can call the control pulse, such as the modulation pulse, arriving at a different time delay here. And the dashed black line here is indicating the laser, the shape of the laser, and then the colored line that follows here is the fluorescence, the emission. So we can see that the spontaneous emission of the fluorescence is really following the laser and being modulated at these high speeds, also with pretty good distinction. So this is showing that there is indeed some potential for free space optical communication, visible light communications, using these ideas. So I showed you how we can create ultra-fast emission, both from single emitters into centimeter scale areas. I wanted to show you other things that can happen when we use these nanotubes. One thing that we found in particular when we started putting a number of emitters into these structures is to see the emergence of strong coupling. This is the reversible energy exchange between an emitter and a cavity. When that interaction rate is faster than the decay channels in the system, we are seeing this hybrid state. This is characterized by this double peak or double dip in the cavity resonance spectrum, sometimes in the fluorescence as well. And what is neat here is that we see this both from the single cavity structure as well as from a large meter surface. You can notice here for a single cavity, to measure the plasmon resonance in this hybrid state, we're using white light scattering. So we are seeing it as peaks. But for the meter surface, we're doing it in reflectance. So we're seeing it as a dip. But it's really both indicating the plasmon resonance in this hybrid state. And we also did check if we could bleach the dyes and if this double peak would go away. And it indeed did. So that was a nice, nice check. We also varied the gap size and the nanocube size here to map out this anti-crossing behavior. So the dashed horizontal line here is the dye absorption, and then we are varying the plasmon resonance, and then we can see at this double peak emerging here, and this characteristic anti-crossing. What we found was that we can actually also actively tune these structures in and out of this strong coupling regime, which I think is pretty cool. And a way we found we could do that is actually by changing the temperature, because we use these polymer layers in the gap, and it turns out that these are actually sensitive to temperature. So they are slightly expanding and contracting the temperature, water emerging and re-emerging into the structure. So you can see we go from a single dip here to this double peak, so we can really tune the strong coupling in real time. Next, in all these experiments so far, we only use the fundamental resonance of the structure, but we also have a second order mode. So here is showing the fundamental mode, but we also have the second order mode that we typically haven't utilized. But it's actually very convenient to have two resonances to play with, in particular for two-dimensional materials. And we tested it out in monolayer MOS2. So here we have a weak absorption and a low quantum yield. So we set out to see if we can simultaneously enhance both using these two resonances. And it so happens that the fundamental resonance is overlapping with the emission here, so we can enhance the quantum efficiency as well as the spontaneous emission rate. And the second order mode allows us to enhance the absorption. And In addition to enhancing that, so that allows us to see enhancement around 2,000 times in the A exciton emission. So this top panel shows the spectrum from the intrinsic spectrum from monolayer MOS2 on silicon dioxide, a native substrate, and it has an A exciton here and it has a weaker B exciton. But what we found is by changing the size of the cubes, we can completely modify how this fluorescent spectrum looks. So we can mainly enhance the B exciton or the A exciton, or we can enhance both, depending on where we pick the plasmon resonance to be. The little arrow here is indicating where we put the plasmon resonance. And in this case, we could enhance the A exciton a couple thousand times, but the B exciton about 6,000 times. This is because the B exciton is intrinsically has a lower quantum yield, and when we enhance it with a plasmonic structure, we're enhancing the quantum yield to be about the same in both cases, at around 50%. So that means we can enhance this weaker B exciton more. So I think it's exciting to see how you can use the plasmonic structures also potentially to study even weaker exciton states in two-dimensional materials. Finally, when we are looking at optical properties that are arising from our artificially created environment, it's fun to think about how can we modify this environment to create reconfigurable structures, which is really something you can't do in the bulk in the same way. So here we looked at all optical switching using photoswitchable molecules. So there's these neat molecules called spiropyrin that when you apply UV light to it, it turns into a different isomer that's called myrocyarin. So it's a ring opening, and when you apply visible light, it will close again. So it's a reversible process. And when we embed that in these nanogap structures, it allows us to do a reversible tuning of the plasmon resonance, because we're changing the index of refraction of this gap, and there's also some resonant coupling. It's complicating things a little bit. But we can tune the plasmon resonance up to about 70 nanometers with large on-off ratios here. So you can think about utilizing this potentially for reconfigurable devices, advanced coatings, and also be a route to actively tune radiative processes of emitters. So I want to change gears a little bit, but utilize some of these same ideas where we can very efficiently couple incoming light into small mode volumes and see how that's modifying the way that we might think about thermal photodetections. So it was sort of an obvious thing when we have these structures, we are very efficiently absorbing light, that it would be nice if we could incorporate some sort of detection mechanism. And there's indeed a large field of how can thermal detectors be combined with nanophotonic structures to improve their properties in various ways. There's beautiful experiments here using bolometric detectors where there's shown very fast response times, but these were typically done at cryogenic temperatures and required careful fabrication. It's not spectrally selective, I believe. These thermoelectric detectors, which were able to speed up the response time a lot for, this is a spectrally selective, using resonant nanophotonic structures with speeds about 300 microseconds. And then there's pyroelectric detectors as well that was shown to be spectrally selective, but have very slow response times on the 100 millisecond scales. So we're thinking about if there's a way that we can make some thermal detectors that can both be spectrally selective, fast, and room temperature, and nice if we can have a relatively straightforward fabrication of those. So we were looking back at, so in this case, to utilize plasmonics, the pyroelectrics materials are actually very well suited because pyro, yeah, it means heat. So it's combining heat with electricity. It means heat in Greek. So it's combining heat and electricity. So it's very useful for plasmonics because it's typically generating local heat in these metals, and then we can use that to generate a current. So these are not as well known. The way they work is that they have a temperature-dependent spontaneous polarization in the crystal here. So this is for where you have no temperature change, but when you have a small temperature change, the polarization in the crystal is slightly changing, which is causing a current to flow here. And this is the same family of materials as ferroelectric and piezoelectrics that are much better known, where you can change the spontaneous polarization with the electric field or by strain or pressure. But for the pyroelectrics, we are changing the spontaneous polarization by applying heat. And we want to then try to see if we can make it spectrally selective, so utilizing these nanocube structures. So we utilized them in the past for just picking a plasmon resonance that is overlapping well with the emission characteristics of our system. But we can also make these structures without putting any emitters in here and demonstrating how we can make pixels out different spectral bands. So what we've done here, as you can see, make small pixels. In this case, just a small, each pixel is an array of 6 little squares here. And if you zoom in, each of these squares is consisting of nanocubes of a particular size. And the size of the cubes and the gap thickness is pixels that we can change the plasmon resonance here. And each of these is done with a photolithography step. So we are combining layer by layer deposition and photolithography so that we can deposit cubes to only adhere in one area and not another area. But if you want to make a lot of colors, more than these 6 or 20 or so, it might get pretty cumbersome. So we also came up with that you can do combinatorial colors, similar to a red, green, and blue scheme, where you're basically varying the fill fraction within a cube of the different color bands here. And that allows you to create combinatorial colors, where we showed you can get up to about 10,000 combinatorial colors. So now that we can see we have a way of making spectral filters, now we want to integrate that with pyroelectrics. So what we're doing here is depositing a emitter surface directly on top of a pyroelectric material. In this case, we are using aluminum nitride. And here you can see from some simulations how the heat is moving in the structure. So this is a 1 picosecond after excitation. We can see we mainly have heat generation in the gap here, but then it's diffusing down into the pyroelectric layer underneath, changing the polarization and causing a voltage. And this generated voltage depends on the resistance, the detector area, the pyroelectric coefficient, and the temperature change. And you can see we could also think about putting the material in the gap here, but that was trickier to fabricate and would be a very thin layers. In this case, we are utilizing this to act, to trap the light and to create the spectral filter, and then the heat is diffusing down. So first we wanted to see if these spectral filters actually work, if you can actually control which wavelengths of light is detected by just changing the size of the cubes on top. And what we see is that the photovoltage does indeed follow these unshaped filters. So the top here is showing the reflectance spectrum. So it's indicating the plasmon resonance of 4 different structures here. So we used 100 nanometer cubes, 125, 135. And in this case, we also did a test where we fabricated cubes with electron beam lithography that were much larger, 250 nanometers. And what we are seeing is that the photo response, photovoltage or responsivity here is following this unchipped filters very well. So we can see the blue here is corresponding to the blue, the purple to the purple, and the red to the red. So we can see we are indeed can get a photovoltage that follows the absorption of the plasmon resonance. And we can create spectrally selective detection from 660 out to 2000 nanometers. But I think the real beauty of this is that there's really no limitations on the wavelengths here. It's a thermal detector. We can make nanoscale structures really to absorb at any wavelength. So you could have a very beautiful detector that could be sensitive across the entire wavelength range theoretically. So we thought that was a nice demonstration, but what was really the surprise in these experiments was that we could see that the photo response was also fast. So remember with the pyroelectrics, I showed you often it's in the millisecond time scale. So it's a very slow response, and it has really limited the commercial applications. So what we found here was that we have an ultra-fast detection speed. The way that we measure that is we use, again, a pulse laser that hits the sample here at time 0. And then we are just measuring the photovoltages as a function of time to map out this response. And we can see initially we have heating that's depolarizing the aluminum nitrides. Then we have some cooling that happens here, and we have some oscillations, which are likely due to just vibrations in the structure here. But what's important is this very fast rise time, and that's the way that photodetectors, the speed of them is typically characterized as by 10% to 90% of this entire peak. How fast does that rise? And in our case, over 700 picoseconds. And this is really limited by our instrument readout. It's not limited by the detector and the material that we fabricated. So this is limited to around 500 megahertz, which is right where we are. And our simulations that were done in collaboration with Xianghui Fan are shown in red here. And these are convolved with the instrument response, which means if the instrument response was faster, we would also have a faster expected response. And this is much faster than any of the typical pyroelectric, spectrally pyroelectric detectors. But if we compare it with any other spectrally selective thermal detectors, it's about 5 orders of magnitude faster. So we're really getting into a new regime. And that's also what I was alluding to in the title, is how can we use these new nanophotonic structures where we have critical dimensions and almost atomic scale to be able to make new ultra-fast devices. We wanted to understand the speed in a little more detail. So in that case, to do that, we modified the detector size because, as I mentioned, there's a dependence on the area here. So we can consider these structures as basically a parallel plate capacitor where the bandwidth is 1 over RC here. So you could see it inversely proportional to the area. So as we get to larger areas, the bandwidth or the speed is going down. And that's also what we see in the experiment on the left here. This is a 75 micron detector diameter, and it goes up to 100, 250, and so on here. And you can see the speed is slowing down significantly. But what's really exciting, I think, is that these larger detectors, yes, sure, they're limited by the RC time constant, but this regime of very small detectors to try to figure out what are the limiting factors here, because right now we're limited by the instrument response. And we can see that the speed here as a function of detector size follows the expected behavior. So we started to think about how fast the response could be. We did simulations with Xianghui Fan at Stanford as well. And we could see from these very simplified simulations at the moment, but that they're showing very fast response times. So we have the electric field here that we can put into looking at the heat that's generated and the temperature change here at 1 picosecond and at 40 picoseconds. And what we find is that it's the rate of temperature change here. So it's this spike here that gives us the response time. So this is, if these simplified simulations can be believed, that there's potential for much faster response times, potentially into the 6 picosecond rise time and 25 picosecond full width half max. We did do previous pump probe studies using transient absorption in this Nature Communication paper showing fast plasmon thermalization, 10 picoseconds, but there might be grain boundaries always in physical systems. There's a lot of other effects going on. I doubt we can get this far. That would be pretty remarkable, but I'm sure that we're not at the limit. So we're somewhere between the 700 picosecond and down to the tens of picoseconds. Next, I think it's interesting to think about some of these real-world applications too. So it turns out that hyperspectral imaging, where you have the spectral selectivity that we could potentially imagine doing here, could be very useful for a number of applications. So hyperspectral imaging, and there you typically collect a wavelength spectrum over a broad wavelength range, say 400 to 2500 nanometers. So you may collect a wavelength spectrum here as seen, and then you do that at different wavelengths, spatial map, and then you do that at different wavelengths, such that at each pixel here, you can get a reflectance spectrum. So what light is absorbed, what light is reflected. And this is referred to as a spectral fingerprint and uniquely reveals material and its composition. So we can start thinking about using these multispectral pixels to be able to do that sort of ultra-fast devices. And there's lots of applications of hyperspectral imaging. It's used for understanding behavior and health of crops for precision agriculture. It's used to detect cancer tissue and image-guided surgery. It's used for food and water safety. Several people from this sector has contacted me to see if we can make cameras for them and computer vision for automated systems. I think it's very exciting to think about how these deep nanoscale structures actually might be able to be useful in a number of different areas. So I wanted to acknowledge and thank my wonderful group at Duke, my collaborators, as well as funding sources. And we do have postdocs positions. If anyone is looking for positions, please contact us. So I wanted to summarize the talk. So I showed how we could create ultra-fast emission from single emitters to centimeter scale areas. So these were the single emitters, and then we can do this very fast modulation. We also showed strong coupling, utilizing higher order modes for this spectral tuning of two-dimensional materials, and also showed dynamic tuning. Then I showed you these fast thermal photodetection, which we were trying to indicate here, the change in polarization underneath, as well as color pixels and the fast photoresponse. We also did do a review article in this area if you're interested on nanogap cavities that was published in Nature Materials last year. So thank you so much for your attention, and I would be happy to take questions.
Okay, well, thank you. Thank you so much, Mike. And clearly we made the award to the right person. This has been a truly inspiring lecture. So many thanks from the audience here. So what I'll do is to invite the audience to enter any questions that they have into the chat for Professor Mikkelsen. And in the meantime, I'll start by asking a question related to strong coupling. You alluded to and you described one instance where you observed hybridization and splitting and strong coupling. I'm wondering, in the results that you showed at the beginning, does strong coupling always come into play, or do you end up in these caps where you have very large enhancement of emission rate? Is the spectral shape preserved in some cases, or what is the regime where strong coupling matters and where it doesn't matter?
Yes, that's a good question. And typically we don't see that spectral that dip. So typically we seem to be in a regime where we have, let's say, significant enough losses to not get into a strong coupling regime and can just get the ultra-fast continuous emission. We saw the strong coupling in a few cases. We saw it when we had packed this large amount of emitters in there, which makes sense because the strong coupling, depending on the number of emitters, or the square root of the number of coupled emitters. So you do expect when you have more emitters that you will get into that regime much easier. We did actually also observe it for single emitters, I believe, that we saw modifications in the fluorescence spectrums with double peaks in that, as well as in the plasmon resonance. And that was a little bit harder to model because we wouldn't quite expect that from our geometries. But thinking back, and we never published that because we couldn't quite figure out what was going on. But I think what's going on is likely some small atomic protrusion, small variation that's allowing us to get even larger hotspots than you would expect from this idealized planar structure. And in those cases, then we can get into the strong coupling regime, likely for single emitters as well.
Yeah. And the second question that I had from your talk was about the temporal modulation. A very interesting experiment. You showed a pump probe experiment. And I was wondering, I wasn't quite clear what the modulation mechanism was there. So you have a pump pulse that's exciting the emitters. And then what is this probe pulse doing? What a physical effect is then causing emission?
Yeah, I'm sorry that I went over that too quickly. So it's basically doing the same thing as the first. So it's just re-exciting. And so it's spontaneous emission that happens again. So it's seeing how fast can we repeat the spontaneous emission to occur. Okay. So first, we are exciting electron hole pairs at the case, like exciting electron hole pairs the case. But yes, you could think about doing other types of modulation. That would be very exciting. But in this case, we just wanted to see how fast can we re-excite the structure.
Okay, yeah. And then finally, in these cavity experiments, the orientation of the dipole also determines how it couples to the field. And you can calculate, you've done very nice calculations of the field. I assume in most of the experiments that so I guess the question of how the dipole is oriented is another important question. What is your perspective on that? I guess for a spherical quantum dot that can be polarized pretty much in any direction, other emitters probably have a preferred dipole orientation. How do you take this into account in your experiment characterization and planning?
Yes, that's a very good question, and that's very important. We often we measure it if we can, right? So we can measure the dipole orientation. Often it can be tricky to control the dipole orientation. There's chemical ways that you might be able to control the dipole orientation. You may be able to pick emitters that has a preferable dipole orientation. For quantum dots, I think it was pretty much random, so that was taken into account in that way. It also does have some in-plane fields, so we could see. First, we thought we wouldn't really see much enhancement from the 2D materials, but when we did the calculations, we could see they had rounded corners of the cubes, and we actually do have some not negligible enhancement in the in-plane direction, so that's useful as well. And otherwise, you can start thinking about, I think this is really just a general way of thinking about nano gaps, structures, and large field enhancements, but there's a wide range of ways that you can design other plasmonic geometries, right? If you have some specific structure, that material you're interested in enhancing and modifying, you can think about how do we want to make large field enhancements so that it's coupling preferentially to that structure.
Okay, yeah, good, great. Let's see. So if members of the audience have a question they would like to ask, please feel free to answer this or pose this in the Q&A. So I don't know, Roman, if you have a question.
Maybe in the meanwhile I can jump in. So this is a bit related, I guess, to the answer you gave to Harry's first question. And so in all this configuration where you have the nanocubes in front of a mirror, so when you nicely represent your system, you show a flat mirror. But in reality, when you look at the SEM images, you see there is some roughness. So I was wondering actually whether the roughness is a limiting factor, is that, or on the opposite, this is actually an asset for you to achieve like higher light matter interaction.
Yes, that's a good question, and something that we have certainly studied in great detail. So typically we see if the film is too rough, it's not ideal at all. So if this film gets too rough, we end up and not being able to see a large area plasmon resonance because the variation from cube to tube is just too great. So typically we have a roughness less than a nanometer, so AMS roughness. And in some cases, when we want it also smooth, we might do something that called template stripping, where we evaporating the metal on top of a very smooth silicon wafer, and then we can peel it off, and then we can use that as our starting surface, and then we can get AMS roughnesses down to like 0.3 nanometers as measured by AFM. So smoother is definitely good. It would also be interesting to look at the effect of single crystalline substrates. I know some other groups are starting to do that, and that might have an effect as well. I guess we had a little bit of look at that by changing the cubes that are single crystalline now to made with EBL, and we didn't see a big difference. We sort of thought we would see a bigger difference than we did. So it might be that the 0.3 nanometers or so is good enough, but it might also depend, of course, on the phenomena that you're looking at in particular.
Good, thank you.
Okay, so we have a question from the audience here, and that is related to the issue of order. And you've shown now nanogaps. Most of the examples are ones where they're colloidal nanocubes, and the resonances are proportional, of course, to the geometry of the cube. But in most of the examples that you showed, I think, as I understood, most of them were are randomly oriented, the cubes themselves, as you put them down in the fabrication process. And what is there any spectral filtering or spectral modulation that comes about from ordering of cubes? Either if you've ever seen that in practice, or whether you've thought about methods for fabrication that would allow you to create ordered arrays?
Yes, that's a good question. Thanks for that question. So there's a couple of ways that you could have potential effects emerging from the order. One is, of course, if the cubes are close enough that they're actually coupling, so you have intercoupling cavities, and we're not quite close enough to do that. That's something that Andrea Tsao at UCSD had a nice paper in Nature Communications a few years back, where she saw if you had the cubes about 30 nanometers apart or less, you start to see coupled modes and cavities in between there. Our cubes are not quite as random as they look, actually, because they have this polymer coating around them that's slightly charged. So it means that they actually has some repulsion. So we actually did analysis of the mean cube spacing, and we could see that there's actually some order occurring, but of course not in the orientation. So typically they're around, let's say, 200 nanometers or so apart. So we don't have expected much coupling in between them, really.
Okay.
The other way that could be interesting is, if you have arrays. So we have started doing that. Ways of doing that pretty simply is either by just DPL. We can do stamps to do that. We have started thinking about making more interesting structures. We actually had one paper where we did a bullseye around emitters and then had a cube with that, so that we could have more control and narrow the radiation pattern even more. And we are thinking about, if you can make cool unit cells where you can have more control of the behavior, because we have some light that's lost, right, from non-radiative decay candles. So if you can reuse that in a smart way, that would be very interesting.
Okay, well, so I want to have the audience join together here as we're approaching our time, and thank Maiken for the beautiful lecture, and which spanned from emitters to detectors and discussion of strong coupling. Hearty congratulations on the award of the ACS Photonics Young Investigator Award, and it looks like there's a very exciting future here for this work.
Thank you again for this opportunity, and thanks so much for the award.